at this time we have a strategy. We went to 5.6 and we built an inequality strategy that works all the time. So you're more than welcome to use that same strategy in 1.7. However, 1.7, one of the first type of inequalities they discuss are what we call linear inequalities. There's some nuances about that that are important for you guys to know in some other areas of math. So I want to make sure we address that, you're aware of it, and that way if you ever come across it in a future math class or in our class, you know what's going on and you're comfortable with it. The good news about solving linear inequalities is we can actually use the same idea to solve equalities. And that's basically way back when we're essentially using the golden rule. So whatever you do to solve the equality, you solve the inequality. And so that makes them very easy to solve. So basically I think we did this, was it 1.1 or 2.1, somewhere back in there. We solved, I think it was 1.1. Or 1.2 actually, where we solved that. So whatever we did to solve the equality, we can solve the inequality the same way, right? There is only one nuance though. So let me put this in red. We have to be careful, right, when we multiply or divide by a negative number. That's the only thing we have to be careful of. What we commonly have to do is we have to flip the inequality. So let me address this idea, and let's take a look at something that we know to be true, and then just start multiplying and dividing negatives to see how it becomes untrue unless we flip the inequality. So I think we could all agree that 2 is less than 5. Even when I look at a number line here, right, here's 0, somewhere there's 2, and down the line is 5. So clearly that is a true statement. But if I took this inequality and I decided to multiply both sides, let's just use -1 because it doesn't really matter if it's a bigger negative number or not. If I multiplied both sides by -1, here's what happens. This side now becomes -2, this side becomes -5, and if we kept that the same, we now no longer have a true statement, because visually what ended up happening is -2 is now right there, -5 is over there, and we now know, right, that -2 is actually bigger than -5. That keeps it a true statement. So notice by multiplying both sides by a negative, I flipped the inequality, keeping it true. And visually we can see literally what happened, right, as here we have the relationship between 2 and 5, and then by multiplying both sides by a negative, we effectively introduced the concept of opposite. So 2 flipped over to here, 5 flipped over here, and so there's literally a flip-flop, right, in their relationship to each other. And because there was a flip-flop in the relationship with each other, that's why we have to do a flip-flop with the inequality that we're doing, so that my inequality remains true. This would have happened the same way if we'd have divided both sides by a -1. Again, it doesn't really matter if it's -2, -3, -4, -5, right? This is now -2, this is -5, so there's been a flip-flop in the relationship to each other. Effectively, by multiplying or dividing by a negative, we introduce the concept of opposites. So if I was negative, I'm now positive. If I'm positive, I'm now negative. Either way, right, I flip-flop my location across 0. And that means I have to flip-flop my inequality to make sure I'm true. So the good news is that solving inequalities, we're going to keep playing the golden rule, add, subtract, multiply, divide, the same thing from both sides like you would an equality. However, when we ever find ourselves in our work multiplying or dividing by a negative, we have to, here's the new idea, we have to flip our inequality. So that's a little bit different than the equality when we're solving inequality. And that's basically it. That's the one big nuance in terms of solving these things. So there's the groundwork. With that groundwork out of the way, let's go solve some linear inequalities. I know these are all linear inequalities because that's a line, right? mx plus b. I've got 2 lines here. 2 lines and 2 lines. So everything's of that form, y equals mx plus b. So if I was to graph these, I would be getting a bunch of lines. So how do I solve them? Just solve them like they were equalities. So I begin this journey by subtracting both sides by 3. That gives us 2x is less than 10. I'm not going to flip-flop this because I'm not multiplying by a negative 3. I'm subtracting 3 from both sides. Multiplication and division is the only thing I have to worry about. Divide by 2, and we get x is less than 5. So again, I'm not flipping the inequality because I am dividing, but I'm dividing by a positive, right? I only have to worry if I divide by a negative. So inequality-wise, my solution is negative infinity to 5. So let's verify that. When I go look at this, I've kind of preloaded this in. This nice greenish color is the line 2x plus 3, and 13 is that solid line right there. And you can see that right about at 5, right? So there's 5. They are crossing each other. There's where they're equal to. And the graph of the line, 2x plus 3, is in fact below, right? Less than the graph of 13. So everything to the left of 5, right, makes it true. Everything to the right of 5 would make it untrue if we were using what we learned in 5.6. So we got that guy basically verified. All right, what about the next one? Again, a little bit more going on, but just keep solving it like I would in inequality. So perhaps I subtract 3x from both sides, and while I do that, I subtract 5. There's a lot of negatives there, but I'm not multiplying or dividing by a negative. So the inequality stays the same. We end up with a negative 5x on this side, and that looks like a negative 7 on that side. I'm going to change colors because I am dividing, but look what I'm dividing by, right? I'm dividing by a negative. So that means this side becomes x, this side becomes 7/5, and because I divided by a negative, I have to flip-flop the order of my inequality. All right, so that means our solution is basically negative infinity to 7/5 because we're less than 7/5. So there's the nuance there. I'm playing the same golden rule we did back in 1.2. We add, subtract, multiply, and divide whatever we want to both sides, but we just have to be careful when we multiply or divide by a negative. Here that never happened. Here it did. I flip-flopped. How do I verify this? Let's go look at a graph. So here's the graph of 5x minus 2, right? So that's kind of in black there. And then here's the graph of 3x minus 2. And we do in fact see that, oops, yeah, yeah, I got it right. We do in fact see that this graph 5x minus 2 in black is actually on top, right? It's greater than the graph of 3x minus 2 that's in red. And that's occurring right about 7/5 and to its left, which is the inequality that we got, right? If we go to the right of 7/5, right, if we hadn't changed the inequality, we'd be wrong because the graph of 3x minus 2 in red is actually no longer below the one in black. So we're solving the greater than. All right, so there is basically the video proof or the graphical proof. Okay, so we're already 8 minutes into this. I've already covered a lot of ground. Next, we got some fractions to contend with. So how about I cut away to a new video and we'll worry about those fractions in a nice fresh video. Talk to you guys soon.